Hello and welcome to my channel. And for me too, it's a coming back because today the topic I will study on has already been studied in PCTF platform in depth. Of course, it was meant for the teachers, so naturally it was a bit lengthy and in-depth study in each session, and probably that's why some of my younger colleagues, brothers and sisters, they have requested me uh, to make 2 or 3 videos on this topic in my own way, so that they can be more students friendly, uh, so that they can easily use in their classes, very specific to the point as per the requirements of the syllabus. Of course, they are talking about Calcutta University syllabus. In other universities, the experiments are there, but not as such in this format. So, our topic today is computer experiments using numerical methods, of course, in ForTran. So, today I will be delivering part 1. So, as you know that it consists of 2 parts. One is use of numerical methods. So numerical methods that to be discussed, but that corresponds to core course theory part. But today we are discussing a paper which is actually a lab course experiments, which is programmings. That is the corresponding lab of the core course theory, which is numerical analysis. So actually there are many methods for a given problem, many numerical methods that you can think of to solve a particular problem. Then the question is which one to apply. Here we will be guided which one to apply. We will be guided by our corresponding theory courses. That means in that course what are the numerical methods we have to discuss, and accordingly we can apply those methods in our practical courses. So let us have a quick look of what are the types of different types of programming required for our experiments and what are the corresponding numerical methods. For experiment 1A and B, it is basically the programming of roots of equation, finding of roots of equation, and the method will be used. Of course, there are many methods, but we will be using iterative method, mainly Newton-Raphson method. Experiment 2A and 2B, it requires numerical differentiation, and out of 3 types of differentiation formula, mainly difference, central difference, backward difference, and forward difference formula. For convenience and for mostly what are more frequently used one is the central difference formula. So we will be here in our cases central difference formula. And experiments 3A, B, and C, it uses numerical integration, and we will be using either Simpson's rule or Simpson's 1/3 rule and trapezoidal's rule. So these are the outline. A total of 3 types and 7 experiments we have to encounter. So what are the experiments? So let us see the names of the experiments. Experiment 1, type 1, which is basically on roots of equation by Newton-Raphson. It consists of 2 experiments. 1A, volume of van der Waals gas. That means finding the root of the van der Waals gas equation of state. And 1B, pH of a weak acid. And then experiment 2, numerical differentiation. Again, there are 2 experiments. 2A is finding change or variation in pressure for small change in volume change for van der Waals gas. And 2B, it's a potentiometric or you can say pH metric titration. And then comes experiment 3, numerical integration, Simpson's or trapezoidal. 3A, entropy change delta S calculation from heat capacity data. 3B, enthalpy change from heat capacity data. And 3C, probability distribution in relation to kinetic theory of gas. And using that distribution function to evaluate the mean values of different quantities. So these are the experiments, and our way of strategy for narration on the experiments is like this. First, we'll start what the experiment is. Of course, then we'll touch the physical problem. What is the physical chemical problem of that experiment, and then we'll discuss the mathematical problem. That means the physical problem is modeled to be a mathematical problem, and then it gradually goes to a computational one with the help of course numerical analysis. And so what is the computational task, and then we'll see the program along with its algorithm or flow of structures, structure of flow, and what are the inputs required and what are the output we are going to get, and if any conclusion is there to make. Of course, numerical analysis plays a big role here, but that is part of the theory course. So here we will not discuss in details, rather we will assume that those methods, required methods, and here we will only give a brief outline of the essential part of the numerical analysis required for different programming. So let us one by one go for the three numerical methods that to be used in our whole course. The first one is of course Newton-Raphson method, an iterative method to solve an equation fx equals to 0, finding the root. So what is the basic strategy? It starts with a guess, initial guess, right? So it's a function of x, so we have to have an initial guess, say x0, and then you have to modify the x value in an iterative strategy way by this formula. So if it is the nth stage or nth step x value, and it is obtained from its earlier value x n minus 1, and using this ratio fx by f prime x. However, f prime x is nothing but the first derivative of the function at that point. So this is as simple as that. You are getting the nth x value from n minus 1th x value, provided if you can calculate the function value at the n minus 1th value point and its derivative also at that same point. So that's all about Newton-Raphson. But how long you will go on iterating? That means in terms of computational language, what is the criteria of stopping criteria or checking criteria? How long you will continue? The answer is that at each step of this evaluation, you can evaluate the difference between these two, or rather the absolute value of the difference between these two consecutive x values, and if it is less than epsilon, which is a very small number, predefined small number, as small as say 10 to the minus 4 or 10 to the minus 5 as per your convenience, then it means that the values are very close, so that means no further modification is needed or possible, so we'll stop. So that is the stopping criteria for this iterative method, Newton-Raphson. Now what type of function we are talking about, fx equal to 0, that we are going to solve this by this method? In our case, it's a simple polynomial kind of equation, either cubic or quadratic, right? So fx may be like ax cube plus bx square plus cx plus d equals to 0, and naturally f prime x, the first derivative, it would be 3ax square plus 2bx plus c. So that is in general if it's a cubic equation, but in some cases we need to solve quadratic equation, bx square plus cx plus d, that means a is not there. So I can use the general formula, only putting that a is 0. So the same program, the same formula can be used actually in both the cases, quadratic or cubic. So we will see in our real problem how these equations come up. The next one is numerical differentiation. So as I have mentioned that there are forward, backward and central difference formula we can have, but usually, and which is actually the most convenient one, is the central difference formula. So we will be using here in our case only the central difference formula. And it looks like for the first derivative y prime x, it is simply yx plus h minus yx minus h by 2h. So what h is? H is the finite difference between two consecutive x values, right? So you are differentiating at x1, x2, x3, x4 dot dot dot. So two consecutive x values, the difference is called the interval of x, or we simply denote it by h. And what a yx plus h? It is the function value of y at x plus h. Similarly, it is at x minus h. So that would give you the first derivative of y at a point x. And similarly, the second derivative by this central difference formula looks like this. So here x plus h is there, x minus h is there, and also yx, that means the function of y at x, that is also given, required, but not 2h but h square is there. So these are the two formula for first and second derivative. Our task would be for the given y x, that means the given functional according to the problem, you have to take that function value at different points at x plus h, x minus h, or x, and then you just put it in the formula and translate into your programming language and run it. We get the results. Where from we will get the x values and y as a function of x values? Usually we'll get it from the given function. If it's a function given, then we can get it from the function directly. For different x value, we can calculate the fx because fx is explicitly given to you. Otherwise, in most of the cases, what happens, we get the fx value from our experiment, right? Say temperature is our x, and we are finding some parameter or some property, time temperature dependent property. So that would be our experimental value, function of t. So t and that property, function of t, actually x and y of x. So that is the thing. And then finally, it is the numerical integration. So in different problems, integration do occur, but its basic form is like this. So I is the integral, and it, if you evaluates yx dx from a to b. So a and b is the lower limit and upper limit of the variable x, and yx is the functional form of y as a function of x. According to the problem, it would be different from problem to problem, and we solve it. That means we evaluate this I integral value. When it's trapezoidal rule, it looks like this. It means that you are evaluating the function value at some point, initial point, say x0 and xn, nth point. So x0 and xn evaluate the function value. Function is either given to you or obtained from experiment. And then what you do with suffix 1, 2, 3 up to n minus 1. So all these values you evaluate and take the sum and then multiply by 2. So that whole summation would give you the I value finally after multiplication of a factor h by 2. Now a Simpson rule is slightly different, but looks almost the same. Here it is multiplied not by h by 2 but h by 3. Here also you need to evaluate the y0 and yn, but what makes it different from the other one, that here all the other y values were summed up and multiplied by 2, but here the y suffix 1, 3, that is the odd suffixes, are taken together as a sum multiplied by 4, and here the even suffixes are taken together as a sum and multiplied by 2, and that the final result would give you the I by Simpson's rule. So this is numerical integration, and h in both the cases is b minus a by n. So it is an interval kind of thing, that the upper limit minus lower limit of the variable divided by the total number of points, right? How many points you are taking to evaluate these y values. In case of Simpson's rule, there is a restriction that n has to be an even number, but for trapezoidal it can be even or odd. Now we are ready to see the experiment number 1, that is 1a, volume of van der Waals gas. So the basic job is you have to find the root of the equation. What equation? Van der Waals gas equation of state, and we'll be solving this, finding the root by Newton-Raphson. So the problem is taken from McQuarrie-Simon, page 63, reference is given here. The problem looks like finding volume of Van der Waals gas by solving the following Van der Waals cubic equation in V at a given pressure and temperature. So of course you have to choose a gas first. Suppose in our case the gas is argon, and from the text we have taken a pressure, given pressure to be 35 atmosphere and temperature to be 142.69 Kelvin. Of course, for argon gas we have to collect the Van der Waals constant A and B in proper unit from the text. So that also we have collected, and A and B are given like this. So now all the parameters are at hand. Now what we will do, starting from the usual form of Van der Waals gas, that is P plus A by V square minus B into V minus B equal to RT, you can easily manipulate it to show that actually Van der Waals equation, it's a cubic equation like this. So cube, square, V and some constant, and the coefficient coming like this. So for argon, if you use the value of A and B and the given pressure, temperature and the parameter value R, then it can be easily, you can hand calculation, you can show that this cubic equation finally looks like this. Okay, V cube minus something V square plus something V minus some constant. Now our original equation I mentioned earlier that we are taking a general cubic polynomial. So a function of V or X, it is like AV cube, BV square, CV and D. So obviously in our case A is 1 and B is nothing but this value. So what are the A, B value? A is 1, B is minus this value, C is of course this value, and D is of course this value. So A, B, C, D are known to you. You can start with these known values, or you can do one thing, you just give the input of R, T, P, A, B, and this rest of the terms, that means this B, C, D, you can make your computer program to evaluate for you. But here we have actually hand calculated and we are supplying these values directly, A, B, C and T. Now as you know, a cubic equation has 3 roots. So the question is, if you start from an initial guess, you can find a root, of course, but which root, right? So of course this is very important, that it depends on the choice of your initial guess. So really this method doesn't have that facility that starting from any initial guess you can reach any one of the 3 roots. No, it's not possible. So you have to be a bit wise and experienced in or you can have some physical intuition to find the proper suitable guess value to start with. By trial and error I have picked up the right guesses for these 3 roots. So I will show it by one turn, but for you it may not be that easy. You have to go for a number of trial and errors to find the initial guess. Anyway, for Van der Waals gas, that much of physics we know, that the 3 roots, one corresponds to the liquid, that is the maximum value, and the other corresponds to the vapor, that is something 0.07073, and the spurious one is 0.07893. So I think the labeling is somewhere problematic. Liquid and vapor may have exchanged, but anyway, let us see. So this is the information, physical problem and the mathematical problem, and to some extent what we are going to do computationally, right? So computational, if you want to see the logical structure, the steps for solving this problem. So we are applying Newton-Raphson method, right, which tells simply that nth x is modified by this line, right, using the function value and the first derivative value at that x. and we will go on until the difference, absolute of difference, is less than a predefined very small number. So let us check what are the logical steps that we have to incorporate. So fx is a function. I am writing the general cubic function, and naturally prime, the first derivative is 3x square plus 2bx plus cx, right, in general, if it is a cubic one. And then the starting point is you have to read the coefficients of this a, b, c, d, so that you have to supply to the computer. Not only the computer will ask for an initial guess, that also you have to give at as initial guess x or x naught, x0. Then you have to continue a few steps repeatedly. What are the repetition steps? You have to evaluate the function, cubic function, because a, b, c, d are all given here. You have read it, and x that you have started by initial guess, so the whole thing can be evaluated. And similarly, the prime also can be evaluated. So you can calculate the x new starting from x that you have read as initial guess. That means x old, you can say. So x old minus the function by the derivative of the function, that would give you the x new, right? So these are the steps that we will go on doing repeatedly until the absolute of this x new and x old is less than some predefined small number. That means when they are very, very close. So if it is so, then you report that particular x value and the function value. Of course, if you can find the root x, then the function value is going to be 0, because the function is 0 when x is at the root. So you can have a check that you have got the right x or not, because at that right x, fx should approach to 0. And then you stop. If it less than epsilon, then you stop. You need not go any further. But else, if it's not so, in a initial few steps it may not be so, we call it as not converged. Then what you will do, you just exchange that my x old that I read first time is now the x new. That means in the last step what it has got as a modified x, that is x new, you make it to be x old, and you go for continue. Here continue means our again you go to the do steps, and you calculate the function derivative, again you calculate x new, again you check the difference and absolute difference and check whether it's less than epsilon or not. If not, then again else, and you again continue. So after going for a few steps, of course probably after some steps it will satisfy this condition less than epsilon, and then it will stop. So that is the logical argument. Flow of logic occurs in this programming. Now on the basis of that logic, we have written the program. So I will just quickly say about the program. In the first part, you see the read. The computer has read the parameters required, a, b, c, d, the initial guess, and that epsilon small number 10 to the power minus 5, and then it goes for evaluation of a few steps. VID. So it calculates the ideal gas. If had it been an ideal, then that means pressure is given, temperature is given. So 1 mole of gas, what will be the ideal volume? V is RT by P. So I've just translated the RT by P formula to get the V ideal, because I have to compare that, okay, the gas volume that I get from my solution from Van der Waals gas after solving the equation, one of the root of course corresponds to the volume of the gas. So that volume is how close it is to ideal, and as well as to the experimental value. So for that purpose, I have evaluated the ideal gas per mole, and then it write the iterative x and the function value, and it call a function, not function, subroutine subprogram. So it gives in argument list a, b, c, d, x, 0, all the inputs, and it gives you back the function value fx and the first prime. Fxp means first derivative of prime. So it writes the f0, x0 and fx, and then it calculates x, the new x, which is x0 initially what it reads, minus this function by derivative, so that gives you the x new, and then dx means the difference, and it's taking absolute value, so it takes the absolute value of the difference, x minus x0, and then it compares if this value is less than EPS. EPS means this small number epsilon. So then you go to 20, that means skipping this line, go to 10, straight way coming to 20, and it writes converged, pause, stop, end. So it goes out of the program. But if it is not less than EPS, then it doesn't go to 20, then it comes that I was talking about, that now the old x0 is taking the value of x, that is the new x value, and then go to 10 and again comes back. So x0 is redefined. Now that x0 is going into the subprogram again, new x, new fx, new fxp, again calculate the whole lot and check at this stage whether again it is less than epsilon or not. If it is less than, then it goes to 20, converged, pause, stop, end. So this is the subroutine used. The name of subroutine is cal. You can give any name as you like. So subroutine, you see the a, b, c, d, and x is the input, and fx and fxp the according to the formula, fx and fx prime. So that's all about how we have written the program, and now we will show you by running the program. Yeah, here is the program. You see a, b, c, d, epsilon, all values are I have defined. Of course, you can read it during runtime either from a file or through the keyboard, but for my convenience I have written in the program itself. And then it has calculated the VID, and it writes also, and then initial guess for root I, where I goes from 1 to 3, because we know there are 3 roots. So what I want that in a single run of a program, I want to get all 3 roots, of course with suitable initial guess. So for every initial run for I equal to 1 to 3, it asks for an initial guess, you put it, and then it calculates the call the function, I mean subroutine subprogram, and then it goes on repeating the steps depending on the check that if it is less than epsilon or not, then go to 20. That logic I have already explained. This is exactly the translation of that algorithm and exactly the subroutine as I have mentioned. So let me run the program. Okay, so let me run the program, and we are expecting 3 different roots, and it has to be converged. Okay, so initial guess for root 1. So let me give, as I've already given trial so many times, so I know the proper guess value. So 0.25 is one guess, the maximum one that I'm giving, and you see it starts from 0.25 and the function is this as a very big one. Now it goes down and function is changing, it goes next step, it goes again down, the function is very small, and it comes, function is even smaller, and 2167 the function is almost 0, what I expect, and it is converged means the 2 consecutive value is less than 10 to the power minus 5. So even if you go further, then if you want accuracy say of the order of 10 to the minus 6 or 10 to the minus 7, then you can go ahead, but for our case it is good enough. So we can say that this is the x, that means volume V, volume, the root of this equation, and that volume gives you the function value to be 10 to the power minus 10, as good as 0. Now the computer asks for the second initial guess. So let me give you a second initial guess, 0.1, and it gives you, again you see the function value 10 to the minus 11, and it writes converged. That means we have got the second root of the equation, 0.078926, and it is still asking for the third root, and it is say 0.01, and again you will see the converged, and the value is given, and function is again as good as 0. So we can say that by a single run, of course, depending on proper choice of initial guess, which is a matter of your experience and trial and error, I have got all three roots. And let me show you. Let me show you the answer jotted together in the next slide. Yeah. So the initial guess is 0.25, and as you have noted that the answer was coming as 0.2167 like thing. And for 0.1, we have got this value as the final V, that means the root. And from 0.01 initial value, you have got this one. So these three are the roots, that means three are the volume, corresponding to one for liquid, one for gas, and of course the third one is the spurious one, which really doesn't mean anything physically. Another comparison table that you have compared the Van der Waals gas, the experimental value and the ideal gas. Say this is volume comparison, and this is the density comparison. So in both the cases, volume and density, we can easily conclude that the Van der Waals values are closer to the experimental values than those of the ideal gas values. So as a real gas equation of state, Van der Waals is a much better than ideal one and closer to the experimental one, real one. Okay. So that is one important chemical information. Well, I have just shown another problem, but I have not included the program, or neither I will run it. The example is this time again taken from McCurry-Simon, page 57. It was argon, now it is ethane. Pressure temperature is also different, A, B is also different, and if you just run the same program using this cubic equation where A, B, C, D are different from the earlier one. So these are the ABCDs, and if you run the program with an initial guess of volume 0.1, then you will see the function value coming as close to 0, and this is the root, one of the roots. So I have shown just one vapor root, and if you compare again, it will see that it will show you that Van der Waals is better than ideal one and closer to the experimental value as far as density and volume both are concerned. So this is all about experiment 1A. Now we have to go for experiment 1B, which is determination of pH of a weak acid at a given temperature. So first of all, you have to understand that what the real problem is. Okay, that is problem simple, that you have to calculate the pH, right, of an acid. So H plus is there, and you have to calculate minus log of 10 H plus concentration. That's all. But what is the mathematical problem? Mathematical problem is like this. So you have an acid HA dissociates into ions, and at equilibrium the dissociation constant looks like this. And if X is the degree of dissociation and C is the initial concentration taken of the gas acid, then of course you know from preliminary HS level chemistry that the remaining concentration of the three species are like this: CX, CX and C into 1 minus X. If you just put it here, CX, CX and C into 1 minus X, then you can get K as Cx square by 1 minus X. So if you just manipulate a little bit, you will get a quadratic equation in X: Cx square plus Kx minus K equals to 0. So this is the mathematical model. Now the problem has to be transferred or translated into programmatic language by the help of Newton-Raphson method. So here it's a cubic equation earlier, but now it's a quadratic equation. But I will be using the same program, a general formula for cubic, only keeping in mind that no x cube term is there. So A has to be 0. That's all. That's all. So A is 0, and what is B in our formula A, B, C, D? So what is B compared to this formula? B is nothing but this C, Cx square, and here it is Bx square. So B is C. This B is the coefficient in my original equation and C is the concentration. Now what is coefficient C? It is nothing but the equilibrium constant K. And what is D? It is my negative of the coefficient equilibrium constant K. So that means we have got A, B, C, D. 0 concentration of acid taken, equilibrium constant, negative of the equilibrium constant. So we have to put all these values, and if you put, we will get this result. So looking at the result first, then we will go for the program. I will show one problem, acetic acid, but by running the same program, only varying the parameters, a few parameters like concentration, equilibrium constant, etc. You can run it for benzoic acid as well. So I will be showing only acetic acid run, taking 1.0 concentration, molar concentration. It is roughly the order of the domestic vinegar concentration. And we know the acetic acid equilibrium constant or dissociation constant like this. So we have to evaluate that x, right? It's a quadratic equation in x. So finding the root of this equation means you are finding the x which makes the whole thing 0, and that x is nothing but, that we will search actually, that x is nothing but the degree of dissociation. So once you get the degree of dissociation from the solution of this quadratic equation, and then H plus concentration is nothing but C into X. So you know C, you have got X from your Newton raption. So now you get H plus, and then we just take minus log of this concentration to get pH. So that is our target, to find the pH. So this is the chemical problem, its mathematical counterpart, and finally what we are going to do with now instruction is there from computer that run the program too. So let me run the program for pH finding. Well, this is the problem. Again, as I mentioned, that A, B, C, D are given. You see, A is 0, B is 1 molar, so the concentration, C was the equilibrium constant, and D is the minus of equilibrium constant. As obviously EPS is given in the -5, and then you have to give an initial guess, and it again by same logic it evaluates by a subroutine fx and fxp, and then it calculates the x new, and then takes the difference absolute and check whether it's less than epsilon or not, and then it accordingly goes either to say converged and come out of the loop, or you can go to 10, that means goes again for next step repetition. So after getting out of this loop, it now finally calculate the pH minus log of Hc concentration. So that's the problem, and now I will show you by running the problem. So you have to run the program. So it asks for initial guess x0. We know that x0 is going to be a small value because acetic acid is a very weak acid. So let's say 0.01 is the initial guess, and it gives you everything. Only few steps it is taking, and this is the x value, converged x value, that means the root of the equation. It's a cross check that the function value itself is 0, very low. So if this is the x, percentage dissociation fraction, then you multiply by the concentration and then take the log, and you will get the pH to be 2.37. So it gives you the pH 2.37, right? So that's all about our second program run, and the results are here. You can run on your own the benzoic acid case. So we have completed experiment 1A and 1B. Now it's turn of experiment 2, 2A and 2B, and experiment 3, 3A, 3B and 3C, but all those in part 2. So see you in part 2 very soon. Thanks for watching. Thank you.